This is the 9th lecture in a series on single agent search, and we're going to be doing a sequence of lectures here, a sequence of videos. There's actually, in the way I'm breaking it up, there'll be multiple videos per lecture. But we're going to be starting to look at suboptimal search. And so in this 9th video, we're going to be looking at weighted A star, and we'll be looking at a very simple proof that weighted A star returns suboptimal solutions and how that algorithm works. And then we'll be, in the 10th video, we'll be looking at a number of different algorithms that have been proposed that try and improve the performance of weighted A star, but are usually a little bit more complex to implement. And then what we're going to be doing in this video in terms of looking at the properties of A star, weighted A star, we're going to be looking at a simpler version of the algorithm. And so in the following, what will be the following lecture for the class, but the following video, so this will be video 11, we'll be looking at some recent work that tries to quantify a little bit more precisely what can be done and allows us to introduce some very, very simple algorithms that also have very strong performance. So in this lecture, we're just going to be doing two things. We're going to be looking at weighted A star and a little bit of stuff around that. And then number two, we'll be looking at a proof of suboptimality. Okay, we'd like to show what is the actual suboptimality we get from weighted A star. Okay, so to get started with the first question, weighted A star, what we're going to do is go back and look at A star. And so A star, if we recall, uses f, let's say f of n here, is equal to g of n plus h of n, where h is an admissible heuristic. And so far, we're also going to assume that h is a consistent heuristic. And the question is, well, what can we do with this? So this algorithm dates back to 1970. So it's over 50 years old at this point. And a very simple algorithm. And there's a couple different ways we can write it. It wasn't called weighted A star initially, but this is the term that's used ubiquitously today. And so here we're going to use f of n. Sometimes this is called f hat of n, but or f prime of n. F of n is equal to, and there's two versions of this. We could do 1 minus w times g of n plus w times h of n. Okay. Or another way we could write it is f of n is equal to just g of n plus w times h of n. Okay. Now, what about these two different definitions? Well, the first definition here, sometimes this is preferred because it allows us to show that we can get this transition between different algorithms. So if we look at this, if we look here and we say, suppose that w is equal to a half, then what happens is we're weighting g and h equally, and so we get exactly the behavior of A star. And suppose that I make w equal to 0, so this term will all go away, and this term will become a 1 here, and so then we get g of n, which just gives us Dijkstra's algorithm, and then we can take a weight of 0 here, sorry, of 1 here. If we put a 1 there, then that's 0, and we're just left with h of n, and that gives us our pure heuristic search, or our greedy best first search. And so in this formulation, we get this nice transition between different algorithms by changing what the weight is. And so that seems really nice, but this is also a little bit harder to analyze what's going on because we're weighting down both g and h at the same time. And it is equivalent to, or almost equivalent to just putting a w here, a single weight on the heuristic. And so we're going to use this formulation here, but without much changes, we can get this algorithm that allows us to, with the one parameter, switch between Dijkstra's algorithm, A star, and greedy best first search. Okay, and so when we do this here, then we want to step back and say, well, what is the effect? What is the effect of doing this w right here? And I'll tell you what the effect is, and then we'll look at why this is the effect. So what's going on here is that by putting this w in here, or we'll look at practically speaking, what happens? Well, we're weighting the w. So what happens is if I take a step in my search, I expand a state, the G cost goes up. Okay, so G cost is going up. And the age cost, if the age cost goes down, let's just say the G cost goes up and the H cost goes down equally. Well, the difference in the H is magnified by a factor of W. So what's going to happen is that any drop of the heuristic is going to be magnified by a factor of W. And so those states, what's going to happen is the heuristic drops, then the priority is going to drop actually, and not just by, let's say, 1, but by W or by a factor of W faster. And since we prefer states with lower F costs, then what can happen is now we're going to prefer that state far more than a state where the heuristic stayed the same, for instance. And so in practice, what you can think about is if I compare two states, one where the heuristic stayed the same, one where the heuristic dropped by 1, then I'm actually going to be able to take W steps additionally there before I'm going to get the F cost to sort of equalize what happens if the heuristic stays the same, because I get this factor of W in here. Or so W steps where the G goes up, right? So if the G can now go up 3 times as much or W times as much for every single drop of the heuristic when I put the weight inside here. Okay, so, and particularly the lower the H gets, then the priority is going to get, the F cost priority here is going to get very low very quickly. And that's going to drive me to search much closer to the goal than to actually search near the start state. And so weighted A star is a greedy way of trying to get closer to the goal as quickly as possible, and then trying to get to the goal from there. And so weighted A star does work in that way because it is mixing, as we said, it's mixing between being greedy, but it says, look, I'm going to limit how greedy I'm going to be because we're not going to completely ignore the G costs. We're still going to keep some of the G costs in there. And specifically, what we actually can show here is that we're going to get w-optimal solutions. That is, weighted A star with a weight of W is going to return a solution which is no more than W times the optimal solution cost. And one way we can write this, we'll get to this a little bit more in a later video, is we can think of it as a bounding function. So we can, if I have a bounding function, what this is going to tell me is it's going to tell me how suboptimal or what kind of suboptimality I have. And so the bounding function that I'm getting here is basically saying that I'm going to be, so if I'm bounding of some variable here, W, I'm getting something which is W times C star. So this says I'm at no more than W times. We could have other types of bounding functions where I might say I want to be no more than an additive bound away from the actual optimal solution, C star here. And you could imagine other things as well, like maybe being logarithmic or things like that. We're going to focus primarily, well, in here we're looking at weighted A star, so we're only going to look at this bounding function. But the idea here is that we could have different bounding functions that say, how am I being suboptimal? Okay, so I said that weighted A star is going to find w-optimal solutions. You won't find this proof in the original paper by Pohl, but I believe the proof first, or version of the proof first appeared in in a heuristics book by Judah Pearl. And so that was an early textbook on, and it covers a lot of the approaches that you can use for heuristic search in that, and a lot of the proofs of those. Okay, so so this is weighted A star. It should be a fairly easy algorithm, and something that's weighted A star is incredibly popular. If you go look at papers today, they're doing suboptimal search. Almost every paper uses weighted A star as a baseline. And the reason why is once you have a best first search implemented, that this is really just like a one-line change. You just put a W in your priority function, and presto, you have W suboptimal solutions. And so there has been a lot of work on trying to improve this bound, but many of the algorithms that have been proposed have not been widely implemented or used in practice. And I'll explain a little bit about this in the next video, when we're going to go through a number of these algorithms and show how they work, and then talk about some of the pros and cons of those algorithms. But the question we want to ask now is, what can we prove that we're actually going to follow this bounding function, that we're going to get W suboptimal solutions? And actually, before we do that, let's just go ahead and take a look at a video here. And so we can see here now this video is a little bit deceptive because A star is going to run just a little bit faster than weighted A star. But we're going to solve the same problem on the left and the right. A star, because it actually does so much work, we're going to run it a little bit faster. But we can watch here, A star is doing, if we look at the red nodes, so there's a number of nodes that have been expanded. We can see A star has expanded this very, very large region of states in order to reach the goal. And weighted A star is expanding a much smaller region. And if we were to be looking here at what's going on in this search, you should be able to barely see a green line. We can see that a significantly different path is taken by A star and weighted A star. In the weighted A star search, the path goes farther off to the right, where the A star search goes to the left around both of these obstacles. The weighted A star search goes between them. But we can see weighted A star has actually saved a significant amount of node expansions, the states in red, compared to the A star search. So this works in practice, and this was developed pragmatically because there was this attempt to get things to work and to improve the performance of search. But let's go ahead and look and see if we can prove how the algorithm works. Now, when we're doing this, actually, there's something that's important to note, and we haven't really talked about here, or I've alluded to quite a few times, so we're going to sort of start to see this the first time, and that's the question of whether we re-expand a state when we find a shorter path to it. Now, we know that in A star with a consistent heuristic, we do not have to re-expand states. When I find a path to a state and I choose to expand it next because that's the lowest F cost, we know we have the shortest path, and therefore we don't ever have to re-expand states. But here, we've taken this W and put this inflation factor onto the heuristic. And what that means is essentially we've created a heuristic. Well, it is, if we think about this, this is like an inadmissible heuristic because it's higher than the actual heuristic or actual distance to the goal. And the other thing that we've created is we've created essentially what an inconsistent heuristic, because the heuristic is allowed to change to significantly go up and down by more than the G cost, because we've got this factor of W here. Okay, so we're now going to have to think about our search in a little bit different way. And what we're going to do is we're going to assume for right now that in our search, that we do re-expand states. When we find a shorter path to a state, we're going to re-expand that path. So let's imagine here that what we have here is, we're going to go and draw this picture here. So we've got a start state. And let's imagine that what we have is we have over here in the top, we have some optimal path to the goal. So this is optimal. And on the bottom, we're going to have a suboptimal path to the goal. And so that suboptimal path, of course, could be much longer than the actual path. We're going to call this suboptimal path P. And then we have this optimal path on the top up here. And so, okay, first thing, if we just want to talk about the properties of weighted A star, so it's jumping into the optimality, but let's go back and think about this. So is the algorithm, what are the questions we asked? We asked, is it complete? That is, will it find a solution if one exists? And so we're just going to do our regular best first search. We're going to prioritize states by this priority function, G of n plus WH of n. And if we find a shorter path to a state on the closed, now what we're going to do for right now is we are going to take that state off of the closed list and we'll move it back onto the open list. Okay, and given that we do that, the question is this algorithm complete? And as long as the graph is finite, then, and we could be looking at the similar conditions, we can show that this is complete. And basically on a finite graph, any suboptimal, or any ordering of nodes, weighted A star, or any ordering of nodes, as long as we keep all of the successors and put them into the open list, then we're going to be guaranteed to find a solution or a path to every state that is reachable. So weighted A star is some priority function here. We're not changing the nature of the best first search, and so best first search on a finite graph will be complete. Now, in terms of optimal, it's not hard to show that this algorithm will not be optimal, but what we're going to show here is that it's W bounded, or bounding function of W times C star. Okay, And how are we going to be able to prove this? So what we're going to do is we're going to consider this path that we have between the start and the goal, the suboptimal path. And in order to find this path, so this is going to be the path that we actually find, what we have to do is we have to expand every single one of the nodes on P. Okay. And what we want to show is we want to show a property here. We're wanting to show that it's W bounded. So we're going to show that every node expansion here is going to have this property of being at most W suboptimal. And then what we also have is we have this optimal path, and we're going to consider what could be happening for a node on the optimal path as a point of comparison. Okay, so I have some path P, and some path P, and we could call this P of I, which is the ith node. So P is the entire path. P of I is some ith node that is going to be along this path, and what we want to do is prove for any P of I. And so here we're going to do this in a generic way that we could prove for each P of I. And then I have the optimal path on the top. And what we're going to assume here is that, and in fact, we know this, especially when we're doing re-expansion. So let me say this quickly. I'm not necessarily going to write it all out here, but what we want is this property. Okay, let me write this down though. One is that there's always a state on the optimal path on open with optimal cost. Okay, and how does this work? Well, initially the start state has this property. When we expand the start state, then the successor of the start on the optimal path, in this case would be this node right here, would be on the open list, and it'd have the optimal G cost, and so that'd be there, and that would be fine. And now what can happen is we could do any number of other expansions, and particularly what could happen is that I could choose to expand this state and expand it suboptimally. So this node could be sitting on closed with the suboptimal cost. But when I choose to expand this state, I'm going to generate this node, and I'm going to find a shorter path to it, because this is the optimal path, and if I've expanded it suboptimally, then I can reduce the path cost. And I'm going to take it off the closed list. I'm going to put it back onto open, and therefore that state will be on the open list with the optimal cost. And so as long as we have this property of reopening states, then it's very easy to show there's always a state on the optimal path on open with optimal cost. Okay, and so we're going to call that optimal state, we're going to call that N. Okay, so this is the property, and we could do a proof by induction here. It follows the proofs that we did for Dijkstra's algorithm and later for A star. So that's why I'm not going to just go through all those details. But so we're going to call this state N. Okay, and what has to happen for us to find the path P and not expand the full optimal path P is that we have to have the F, and here F is equal to G of N plus WH of N. F of P of I, for all P of I, has to be less than or equal to F of N. Okay, because at every time step, or at least I have to get through this entire path where I expand all the P of I's and I get to the goal, and I never expand all of the F of N. So that is, I don't reach the path, I don't reach the goal along the optimal path. Okay, and we know that every time step we did that, so F of P of I must be less than F of N. And so what we want to derive from this is what is the suboptimality bound that it can exist here. And so this isn't too hard to do. So we're going to say, we're going to keep F of P of I here. So F of the ith state is less than or equal to F of N is this path on the optimal, this node on the optimal path, whatever one that happens to be on open. So that's going to be G of N plus W times H of N. Okay, so we know we're just expanding out what our F cost, our definition of F cost is here. And so the only thing here is I have a W, but of course we could multiply both G and H by W. That would only make this right-hand side to be larger. So that's going to be less than or equal to W times G of N plus H of N. Okay, and W of this node is going to be, so g of n plus h of n, because the h of n is a consistent heuristic, we know is going to be less than or equal to c star. And w, of course, is w. So this is just going to tell me that the f cost of each state p of I, in order to expand this path, must be less than w times c star, the optimal solution. So this tells me that actually for every state, in order to find to have expanded some path to the goal that is not the optimal path, then I know that the f cost of every node here must be less than w times c star. And particularly when I get to the goal and I expand the goal suboptimally versus some other node on the optimal path, then what I know is that the f cost of the goal, which in this case h is equal to 0, so that's just the cost that we find. The cost of the goal is going to be less than or equal to w times c star. So this guarantees that we're going to find a w suboptimal solution when we use weighted A star and we re-expand states when we find a shorter path to them. Now, is this a good bound in practice? Well, if we think about what's going on here, if we look at these steps, so let's just move this up here. If we look at this step here, particularly when we move from here to this step here, what did we do? We actually added a factor of w times the g cost. So what's going to happen here is that w times g, we've added that there. So what this corresponds to is something like this, that we have the start. Sorry, and the other thing we did is, just to point this out, then I can make the full argument, is we replace g of n plus h of n with c star. So we have the start, and what we need is we need a very small edge cost, maybe even a 0 edge cost or some small epsilon edge cost. And then what we need to see here is the f cost of this state to be equal to c star. Okay, so I have a very small edge cost, and then I get a state that is nearly optimal. That has it's on the optimal solution, but the f cost is exactly the cost to get to the goal. And in that case, then now I can have some suboptimal path that goes here that is equal to approximately w times c star. Okay, there's some epsilons here that we might have to deal with, and I'm not gonna just subtract them there. But what we see is as epsilon goes to 0, then this basically goes to w times c star. And so this is how we can be up to w times suboptimal. But it only holds when I only make it a very short distance along my optimal path, and when my heuristic here is basically perfect. And so we can get this w suboptimal solution, but in practice on most problems, our heuristic is not perfect. So I don't actually have f equals c star along the optimal path. And we might go quite a few more edges before we get anything close to that. And therefore, the actual bound here will be much looser than this. It's actually very difficult to find exactly a w suboptimal solution in practice. And so this is a little bit of an inefficiency that exists inside weighted A star, that you have this bound, but in practice, you're almost never going to find a solution that is anywhere close to that actual bound. And so we're not actually going to find w suboptimal solutions. We'll find much better solutions, and then other algorithms can actually take advantage of that property. And so the other thing we might look at here and just notice is that weighted A star is using exactly one priority function, which is this g of n plus w of h of n. And weighted A star actually has two things it must do. The two things it must do is that one must find a solution, and then two, it must show that the solution it's found is within the suboptimality bound. And so weighted A star does both of those things together because it has a single priority queue sorted by g plus w times h, and that priority queue is trying to do both of these things at the same time, both find the solution and prove that it's within the bound. And so it ends up that puts some limitations on how weighted A star works, and therefore a number of people have looked at improvements to that. And so what we'll look at in the next lecture is what are some of the observations that people have made to try to improve the performance of weighted A star. Okay, and so that's the end of this lecture. Hopefully here we now understand how weighted A star works. We're going to come back just to say in 2 lectures, we'll be looking at another group of lectures that will look at a different way of showing the suboptimality of weighted A star. and actually showing that weighted A star does not need to reopen nodes to actually be able to prove the suboptimality bound. But we'll get there in a few lectures.